Hello. Let me get this going. All right. So we've talked about how to start a um, dosing regimen, and now we're going to talk about how to adjust. So we've done a lot of adjusting, just saying doubling or halving when we know that there's been a change in CSS average, but we know we can be more refined than just doubling or halving because that isn't always what's necessary. So how do we adjust once we know, because we're taking a guess with our initial dosing, right? We start our initial dosing, we give a loading dose or we don't, we start our initial maintenance dosing, but then we are gonna maybe draw a concentration or a couple of concentrations and try to figure out how to adjust. Well, we can adjust using the CSS average. We can also adjust using area of the curve. We could adjust using a target Cmax or a target Cmin, so that we can do whatever we want to do. I'm going to just start to target a CSS average. And as you know, we have already anticipated what we're going to have to do with dose rate and dose interval based upon changes in the patient's drugs that we're adding or disease states that we're adding or taking away. So what happens when our CSS target is not where we want it to be? So we draw a concentration and it's not where we want it to be. I'm sorry, I should say, you ask yourself, is it where we'd like it to be? If yes, no change. We leave our dosing regimen alone. If no, we're going to alter our dosing regimen. And we're going to use our good old CSS average, drug in over drug out. If we're giving a salt form, we have to add that salt form in, don't we? So we're going to use our good old CSS average is equal to bioavailable dose rate over clearance. Okay. Right. Oops, sorry. So if we're at steady state, we have a cool trick we can use, or a cool shortcut. So if bioavailability and clearance are linear and in the range in linear, which we haven't really talked about that, but we have to assume that they're linear in the range in that we're working, and there's no change in bioavailability or clearance. So again, if we're saying our CSS average is equal to salt form times bioavailability times dose rate, drug in over drug out. If all of these stay constant, so they don't change, then our CSS average becomes proportional to our dose rate. CSS average becomes proportional to our dose rate. But we have to assume that there's no change in bioavailability or clearance. Then these become proportional. And then we can set up whatever our first dose rate is to get whatever CSS average that we got that wasn't where we wanted it to be. And then we put in what we want our CSS average to be. So this is our target now. And then we can solve for our new dose rate, can't we? So this saves us some time. If we can assume that, so you have to be at steady state, and you have to assume that there's no change in bioavailability, salt form if it's relevant, or clearance. Those all have to stay constant. Then we can say that dose rate is proportional, or CSS average is proportional to dose rate. Wait, first I have to. Okay, so here we have a practice problem. JP is a 78-year-old male who was on 500 micrograms, micrograms of digoxin daily. So the dose rate is 500 micrograms per day. He's seeing yellow halos and was having nausea and vomiting, so he went to the ER. Well, I can tell you because I know this, these are all seeing these yellow halos around lights and having nausea and vomiting are signs of digitoxicity, so too much digoxin in the system. So of course, when he went to the ER and they saw this, they wanted to draw a concentration to see what his level was. And they drew his concentration. It was 3.4 nanograms per milliliter or micrograms per liter. The doctor wants to decrease his dose to target a level of 1, where anything above 2 is toxicity. So we want to shoot for a level of 1 nanogram per ml. So what do we recommend? Well, as long as the bioavailability and clearance are remaining constant and he's at steady state, we can say that dose rate 1 over what we get for our CSS average 1 is equal to dose rate 2 over our CSS average 2, right? Those should be equal because they're proportional. So our dose rate 1 is 500 micrograms per day And the CSS average we got is the resulting, when we gave 500 micrograms per day, we got a concentration of 3.4 nanograms per milliliter, which is the same thing as micrograms per liter. We want those micrograms to be in the same. Well, I guess we don't have to, but I like it better if they're in the same. You don't have to. So what's the new CSS average that we are needing? Well, we need to have a target CSS average of 1 microgram. What the heck? Sorry, 1 microgram per liter, because nanograms per ml is equal to micrograms per liter. So we're going to solve for our new dose rate, which is going to be in micrograms per day, because we have to keep all these units the same. So 500 divided by 3.4. So our new dose rate is going to be 147 micrograms per day. So again, you don't know how this comes, but I would recommend 150 micrograms per day will be our new dosing regimen. We could have gone through and figured out his clearance and then used his clearance to come up with a new dosing regimen. We could do that, but that's a couple extra steps that we don't need to do. So. Okay, so what can alter CSS average? Oopsie. What can alter CSS average? Well, you can name a bunch of things. That's what we've been doing all semester, right? What can alter CSS average? Well, anything that alters bioavailability, which is FA, FG, and FH. We know FH is going to be dependent if it's hepatically cleared. Is it a high or low E drug, right? High or low E. And then you've got all the things that will affect FA and FG. Then we've got dose rate, which we control, right? And clearance. So what determines clearance? Well, it depends. Is it cleared by the liver or by the kidney? And then you have to go through all the things that could affect clearance, right? We also have to think about, in some cases, we need to think about our free concentration if there's been a binding change, right? So changes in bioavailability can affect CSS average, and changes in clearance. So we've got hepatic clearance is, if it's high E, it's going to be affected by Q. If it's low E, it's going to be affected by intrinsic clearance and binding. If it's renally cleared, then if it's filtered, all drugs are filtered. So GFR and fraction unbound are going to matter. If it's predominantly actively secreted, we know we're going to have to look for competition for secretion sites, and if it's predominantly reabsorbed, we'll look for ionization character and concentration gradient and any change in lipophilicity, but that doesn't usually happen. Changes in volume and clearance are going to alter half-life, right? And therefore, peak to trough, half-life K, and what we're going to choose for our dose interval. And what's going to change volume, VSS, is really all about binding, isn't it? Fraction of bound in plasma and fraction of bound in tissue in this relationship. So these are all anticipated drug interactions and disease interactions that will alter what concentrations we see and therefore maybe force us to make dose regimen changes, which is what we're talking about here. All right, so I think that's it. Is that it? I think so. Yeah. All right, thank you. Make sure you take a look at the dosing problems too. All right, that's it.